So good afternoon, everyone. It is 1:30, so we're going to get started. So my name is Archis Gate. I'm the general chair of this conference. And it is my pleasure to introduce the tutorial speaker for today, Professor Shipra Agrawal from Columbia. So Shipra is currently an assistant professor of Auer at Columbia. And her research spans several areas, such as optimization and machine learning, including online optimization under uncertainty, multi-armed bandits, learning in games, and reinforcement learning. And she's interested in applications such as internet advertising, recommendation systems, revenue management, and resource allocation. She serves as associate editor for management science for the area of optimization, and mathematics of operations research for the area of learning theory. Her research is supported by Google Faculty Research Award in 2017, and an Amazon Research Award in 2017 as well, and an NSF Career Award. So please join me in welcoming Shipra to the stage.
Thank you, Arkis. It's a great honor to present this tutorial at Inforums, and I'm very excited to let you know about how great I think multi-armed bandits are and how much progress we have made in this area. So what is the scope of this tutorial? What I want to talk about is really this incredible progress that has been made in almost like last 15 years. The problem has been around for a while, but I feel in last 15 years it has really taken off, where we can solve many unbelievable application areas with it. What I'll do is I'll mostly give motivating examples from applications. I will not focus on applications. I'll motivate the formulations from there. The focus of the talk will be mainly on the algorithm design techniques and also of analysis techniques for those algorithms. So it will be a pretty theoretical talk, though you will see that one reason that multi-armed bandits have been gaining so much popularity is that the algorithms are actually very simple and elegant, so they can often be taken almost as is and applied to many applications. I also want to add that even though I tried my best, there is so much incredible work on this that my references will no way be complete. All I tried to do was give some starting points for you to look at if you are interested in that particular topic in multi-armed bandits. Right, so let's get started. So what is the kind of sequential decision-making problem multi-armed bandits is trying to solve? Because sequential decision-making is very general term as such, right? So let's narrow the scope a little bit. So what I'm trying to think about here is problems where when you make decisions, you are making data-driven decisions, and so you're using past data to make these decisions, but also the feedback from those decisions is going back into the system to make better decisions in future. And this kind of sequential process of feedback loop appears in lots of applications. Like you can think about retail applications where you may price the products in a certain way based on the past historic demand, and then you see how well those prices were taken by the customers, and you may want to reprice it later. Or recommendation systems where based on what kind of recommendations people liked, clicked on, watched movies, you want to improve your recommendations for future. There are more fundamental applications like clinical trials, where based on the reaction of drugs to the patients, you may want to allocate the trials in a different way. Or in robotics, where depending on how the current control policies are performing, you may want to change how the navigation should be done. So this is like a very broad kind of framework where we are thinking about learning from the past decisions to improve future decisions. And what is common in such kind of a feedback loop-based sequential decisions is that you have this very fundamental trade-off between information and rewards. What do I mean by that is that traditionally you would think of taking a decision that maximizes some objective. Let's say it optimizes your revenue, or it optimizes some reward that you're interested in, and whichever decision you believe is the best for that purpose, that's what you're going to take. But now your decision has two purposes. You are not only thinking about whether I can get this customer to click on this movie, but you're also thinking about what kind of information I will get if this customer clicks or not clicks on this movie. Will I get a better information about my customers for future or not? So you have now two objectives which could be competing sometimes. Sometimes you might realize that exploring decisions which may not look good right now may make you a better decision maker in the future. So how do you balance this trade-off between information or rewards, or what we also call between learning and optimizing, or between exploration and exploitation of your knowledge? And that's the key question which Multiarmed Bandit tries to formulate. The formulation begins with this very simple formulation, which is not new at all. It has been around for a while in statistics. So the idea, the name of Multiarmed Bandit comes from a slot machine casino terminology. The idea is that suppose that you had $100 and you walked with those $100 in a casino. Now those casinos have multiple machines, which is what they are calling bandits, rightly so. And each of these machines are rigged in a different way. Okay, so if you put your $1 in one of the machines, then each machine has different chance of giving you a reward. Now you don't know how they are rigged, so you don't know which machine is the best machine to put your money on. And the only way you can find out is by trying it, meaning you have to actually put some dollars and see what happens. And that's only way you can learn about the machine. So now what should you do? Which machine should you try first? How many times should you try each machine before deciding that this is the best machine to go with? Should you do it uniformly, like let's say try every machine 10 times and then decide this is the one I want to go spend rest of my money on? Or should you do it adaptively, like if I tried it 5 times and already I feel this is a hopeless machine, maybe I should abort that right now and focus on other machines. Okay? So this is the question that is the crux of all the applications that I mentioned there. How much of my budget of decisions should I use for exploration versus exploitation? How much should I use for trying out different options and learning about them versus actually start playing, getting money for my decisions? Okay? So how do you balance between these two possibly conflicting objectives? The precise mathematical formulation of the basic stochastic multi-armed bandit problem is this, and the tutorial will go ahead and show you that we can handle much more beyond this basic formulation later on. Okay? So the basic formulation is that you have this discrete decision-making time steps, which I call T equals 1 to T. And each time step, you are required to take one of the decisions, one of the arms. You have to pull one of the arms. So the arms is a terminology from the casino arms. Okay? So you have to pull one out of these n options, take one out of these n decisions. And whenever you pull an arm, you see a reward. You only see feedback from that arm only, and nothing. You don't learn about anything else. And whenever you pull an arm I, the reward is generated IID from a fixed but unknown distribution, IID for that arm, from a fixed but unknown distribution. And we'll assume bounded support. There are extensions to handle other kind of distributions, and with a fixed but unknown mean mu I. Okay. So one of the key characteristics, as you said, is that the only way to learn about an arm is to pull it, meaning that you only see reward from the arm that you pulled. And this kind of characteristics will be present in even the extension that we look at, that your learning depends on your decision. The objective in this kind of formulation is often to minimize regret. And how is regret defined is that imagine a clairvoyant player who knows the distributions of all the arms. So they can figure out which one has the highest expected mean. So somebody knows how the machines are rigged, and they know in expectation which machine is most likely to give me a jackpot. In that case, that clairvoyant player will put all the money on that best machine. And they would get what we call the highest possible mean, which is mu star, the optimal mean. And regret compares what the player, our decision maker got overall in t time steps compared to this clairvoyant player. Okay, so it's a measure, it's a comparative measure to the best someone can do in expectation if they knew all the distributions. Okay. So, so this kind of a formulation also kind of summarizes the trade-off that I mentioned there. Note that it measures the total regret, the total reward that you got overall in t time steps. It doesn't say that how much did you spend on exploration and how much did you spend on exploitation. You are free to divide your time steps between exploration and exploitation. You will be judged on the total overall reward that you got compared to the one who did not need to learn at all. Okay? So I want to, before we go ahead and delve deeper into techniques for solving this problem and its extension, I want to first flesh out like some of the other terminology that you might have heard of, some of you, in when we call multi-armed bandits. Sometimes people think of different things because there are other definitions of multi-armed bandits out there. So this slide will just do take one step back to refer to them, and then we will not talk about these things. Okay? So one common definition of multi-armed bandits, especially in operations research, is the Bayesian multi-armed bandit. Okay? So which is different from the setting I'm talking about. So in the Bayesian multi-armed bandit, it's assumed that there is a prior on these distributions from which reward is coming from. So for example, if for each arm the reward was Bernoulli with mean mu, then you have a prior on the distribution from which mu is generated. Okay? And then we want to optimize reward, expected reward, against this prior. Okay? And regret is also measured over the expectation over prior distribution in addition to expectation over the reward distribution. And that kind of changes the problem because now you can define an optimal way to explore. Okay, there is a concept of optimal way because there is a fixed prior. And therefore, the focus has often been on finding the optimal exploration-exploitation policy rather than minimizing regret. And Gittins index is this seminal result that shows that there is a simple index-based policies for certain cases in the sense that when instead of maximizing total reward, you're maximizing total expected discounted reward. Okay? But this problem of finding optimal policy, even in Bayesian case, becomes quickly very, very intractable. And there has been recent work on minimizing regret even in the Bayesian setting. And this is incredible work. If you want to look at it, you should go to some of these papers. But we will not talk about this setting anymore to avoid confusion. Okay. So now, excuse me. So now that we have defined the basic problem setting, let me just give an outline of the talk. So I will start with the two basic techniques, which I think has formed the focus of lots of different extensions of this problem. And there are other techniques which some of you may know about, but I will focus for interest of time on these two techniques, which is one is the UCB algorithm and the other is Thompson sampling algorithm. Then I will show that how these basic techniques for stochastic multi-armed bandit can be applied almost as is to many, many very powerful generalization of these basic settings. And finally, depending on how much time I get, I'll briefly introduce how they have been used in exciting reinforcement learning settings in recent years. Okay, let's get started. So let's just recall, this was our setting of multi-armed bandits. Every time we want to pull one out of the n arms, and we observe a reward, based on which we can decide what next arm to pull. Right? So what is the problem here? What is the challenge? And I mentioned initially that the challenge is this trade-off between exploration and exploitation, that you cannot take a decision just based on this is the reward that I want to maximize, so let me do a reward maximizing decision. This is because you want to improve future decision. So how does this trade-off come into picture when from this formulation of regret? Okay? So let's see what happens if you don't pay attention to exploration and just thinking about reward maximization all the time. Okay? So why do you need to explore? So imagine that a simpler setting where you have just two arms. Okay, I'll call them a red arm and a black arm. And these two arms have fixed means, Bernoulli rewards, not Bernoulli, sorry, fixed means but unknown means. The first arm has a higher mean, 1.1, and the second arm, the red arm, has lower mean. So the clairvoyant player would play the black arm all the time and get an expected reward of 1.1. If you play any step you play the red arm, there will be a regret of 0.1. So now, what would an exploit-only strategy would do? What would a typical reward maximizing strategy would do if you were not thinking about learning at all? What you would do is, you would do the best data-driven strategy that you can, meaning you will find the best possible estimates from your past observation, and you will do something like a maximum likelihood. Based on the maximum likelihood estimate, you will pick the best arm, which has the highest reward estimate in every time step. Okay? Why is that not a good idea? So here is what happened, and here's where the bandit feedback come in. The fact that what you learn depends on what you do, okay, which arm you pick. So what can happen, and this is the very, very high, like very reasonable probability scenario, almost constant probability scenario. Okay? So imagine that the red arm is actually a deterministic arm. It's just giving you 1 all the time. So there is nothing to learn about it, actually. The black arm is non-deterministic. It can give you different means with different rewards with overall mean 1.1. Now, in let's say first 2 or 3 steps, irrespective of how you played the arms, the black arm could end up giving you some combination of rewards for which the mean is slightly below 1. Okay, it can fall, initially it can fall slightly below 1 because of uncertainty. So what's wrong with that? So after that point, after this point here, when you will do your maximum likelihood estimates of their mean, you will find that the red arm is currently looking better, which means you will play red arm. And that's fine. What happens is that since playing red arm gives you only the information about red arm, it means you will never get over this mistake. You will only keep learning about red arm. You will only keep learning that the red arm has mean 1. And you will not be able to update your wrong estimates about black arm ever. So in order to update your wrong estimates of black arm, you need to explore it sometimes, even if it seems not as good as red arm right now. Because you need to give attention to the fact that black arm could be appearing bad because of the uncertainty in it, because of the noise in its reward. So how do you optimally balance this attention to noise versus attention to rewards? So this is what we call the exploration-exploitation trade-off. When should you play the empirical mean reward maximizer, the maximum likelihood estimate, based on the maximum likelihood estimate or some statistical property like that? And when should you give this benefit of doubt, play less explored actions just to learn about them? You cannot do it arbitrarily, because if you explore too much, you'll be wasting your decision opportunities. Okay? So how you balance this trade-off is how it will define how much regret you can get. And before we go ahead to techniques of doing this in the best way, let's think about what is the best you can do. Okay? What is the best regret you can actually achieve in this problem? Because we are comparing to this clairvoyant player who knows everything about the distribution, right? Whereas we, as a decision maker, don't know anything about the distribution. Now, there has to be some kind of limit to how well you can do, because information theoretically, it's not possible that you don't make any mistakes. Right? If you want to know which is the better arm, you have to play it sometimes, play both the arms sometimes. So there has to be some minimum number of mistakes that you will make, even if you are using the best possible algorithm. So what is the limitation? So in fact, there is very strong lower bounds available for this problem. Informally, the lower bound says, and I'll show the formal version later, is that in fact for any instance, so this is not a worst case bound, it's a bound that defines that if you give me an instance, I can lower bound the number of mistakes that you will make on that instance based on how easy it is to distinguish good arms from bad arms in that instance. Okay? Because in some instances where the good arm is very, very much better than the bad arms, it's very easy to figure out which one is the good arm. But in some instances, when they're close, it's a little more tricky. So this lower bound, which has constants which depend on this separation, okay, which I didn't state here, I'll state them later. So it says that for any instance, any reasonable algorithm, means an algorithm which is at least consistent for all instances, it's not just defined for that particular instance, will play a suboptimal arm, a bad arm, at least omega of log t times. So you cannot get away from that many mistakes, even if you use the best possible algorithm. Okay. There's also like worst case bounds, which are instant independent. So it says that there exists an instance with omega square root nt regret. Okay? So if you can make these instances so tricky to resolve that in the worst case, you could be ending up with that much regret, sublinear regret. So next, I will discuss two techniques which achieve these optimal bounds, actually. So we have two very, very simple techniques in multi-armed bandits which both achieve this optimal, which match the lower bound. Okay. So the first technique, which is the UCB algorithm, which is almost a household name in multi-armed bandits. So the UCB algorithm is a very simple extension of this empirical reward maximization idea. So the idea is that, so look at the every time you want to make a decision of which arm to pick, look at the empirical reward. With empirical reward, I mean, you don't need to stare at this complex expression. This is just saying average of rewards you obtained when you played that arm in the past. Okay, so look at the empirical mean of rewards at any time steps for all arms. Don't use that empirical mean, because if you use that empirical mean, you'll get back to that problem of exploration. You will have only exploitation, right? So don't use the empirical mean. Instead, use an upper confidence bound on empirical mean. So what does that mean? So you know that this empirical mean is not exact. It's not an exact estimate of the actual mean. There is some error in the estimate. And that error can be upper bounded using some standard deviation inequality like Azuma-Hofding by something like this, where n is the number of plays of that arm. Okay? So if you use any deviation inequality, you'll get something like this, a bound on the error in the empirical mean. So you take the error in the empirical mean and you boost the empirical mean by that much. So since you boosted the empirical mean by exactly the high confidence error in the empirical mean, now you have an upper bound on its actual mean. Okay? This UCB term is guaranteed to be above your actual mean with high probability. And high probability depends on like what you use here. Like if you use log t over delta, you get 1 minus delta probability. So now the UCB algorithm simply says that instead of using the empirical mean, use this upper bound. So what they call it as an optimistic bound on the mean, because you're optimistically thinking that it has more reward than what your empirical mean says. So if you were, in that example, if you're playing black and red arms, even though your black arm has a low empirical mean right now, you boost it and say that optimistically I feel it could have a much higher reward, and I will use that to decide which arm I should play. So that is the algorithm. And why does it basically work is that how does it balance exploration and exploitation? So this empirical mean is the exploitation term. By using empirical mean, you are trying to address the fact that you want to play arms with higher mean in the end, right? And this term is giving you the exploration. It's allowing you to explore arms which have low n, which have been not played enough in the past. So if an arm has not been played enough in the past, it will have low value of the number of plays n, it will have a higher boost and higher UCB value to be played. Okay. So why does this work? So can we get a good regret bound based on that? Remember that lower bound said that the best regret bound you can get is logarithmic in time with some constants, depending on the instance, or square root nt in the worst case. So can we get such a regret bound for this simple algorithm? And one of the nice things about UCB, and the reason why it also appears so much in the theoretical literature, it's a very simple and elegant analysis that works for UCB. So how do we analyze the regret? So first let's recall what regret was. So regret was defined as how much do I lose by not playing the arm that the clairvoyant player knows to have the best mean, right? So if the difference between the best mean and the mean of arm I is delta I, then every time I play some arm I lose, this should be T, I lose delta I. So my total regret is delta I times how many times I played that arm. What is the expected number of times I played that arm? So if I can bound the expected number of times that I played arm I can bound regret due to arm I, and then total regret by summing over all the arms. So all I need to do to bound regret is to bound the number of mistakes, the number of plays of arm I for every suboptimal arm. Okay, Ki is the number of plays of arm I in time, capital T. In particular, if I can prove the bound on the number of plays of suboptimal arm I by something like log T over delta I squared, then I will get a regret of sum over I log T over delta I. And that's in fact the very close to the optimal constants that the lower bound implies. Okay, so this delta I is problem dependent, and that's the best in fact that you can do, almost best. I'll refer to that later. Yeah. So then how do we get this? How does UCB achieve this? That the number of mistakes, the number of plays of suboptimal arm is less than log T over delta I squared. In fact, a very simple two-line proof. Okay? So there is, first thing that we already know by definition is that UCB is always above the actual mean for every arm. That's how we always, irrespective of how many plays you have made for an arm, UCB estimate is always above the actual mean. It could be a very bad estimate, it could be very, very above, but it is always above. Okay? Now, we want to bound the number of plays of this bad arm I. So when will be the bad arm I played? When its UCB estimate is above the optimal arm's UCB estimate, right? It has to beat the optimal arm to be played. So when will this happen, that its UCB estimate is above the optimal arm? Its true mean is definitely below the optimal arm. So why is its UCB estimate above? It might be because it has error in the estimates, and then when we boost it by that error, its UCB cross the optimal arm, right? So so how many plays, so as we play the arm I more, the error should reduce. So this boost should reduce. So how long will it take for the boost to become small enough so that it doesn't exceed the UCB estimate of the optimal arm? Okay? How long will it take? So that again, we use very basic inequalities, deviation inequalities, to observe that it will take something like some constant times log T over delta I squared plays of arm I for it to not have this bad behavior. Okay? Why? Very simple. So after these many plays, any deviation inequality will tell you that the mean, empirical mean, will be less than the actual mean plus this delta I by 2. Okay? Delta I is the gap between the mu I and the optimal mean. Okay? So this will happen after these many plays. Also after these many plays, by the definition of UCB, which is this term here, this term here will also become less than delta I by 2, because this term is proportional to the error bound, right? So the UCB boost will also become less than delta I by 2. So overall, we'll see that after these many plays, if this is the true mean, the estimate of mean cannot be more than delta I by 2 point, and above that, after the boost also, UCB estimate cannot cross the actual mean. Okay? So after log T over delta I squared plays, constant times that, whatever happens, wherever the UCB estimate optimal arm is, doesn't matter. At least I know the UCB estimate of ith arm will not exceed mu star. Now, the UCB estimate of optimal arm, irrespective of the number of plays, is definitely above its mean. That I know. For that, I don't need to know how many times optimal arm was played. That is a universal property. So that means since UCB estimate of I is below the optimal mean and UCB estimate of optimal arm is above its mean always, it means that this cannot happen, right? You cannot be thinking that according to UCBs that I is better than I star. So after these many plays, everything will be sorted out. After arm I has been played these many times, yet there will be no confusion between arm I and I star anymore by UCB algorithm. UCB algorithm will almost never play the suboptimal arm. So all I need to so the number of mistakes after which no more mistakes will happen is log T over delta I squared. Okay? So that simply gives the bound on the expected number of mistakes in terms of log T over delta I squared times a constant, and that bounds the total regret, or there should be sum of I over I here, total regret by sum over I log T over delta I. And as I said, this is very close to the lower bound, even in terms of problem-dependent constants. Okay, so this is the whole proof of regret bound for UCB. Right? So the next technique that I want to discuss is a very popular technique that came recently, is Thompson sampling. So it has similar ideas, but a little bit different framework in which you implement those ideas. So the Thompson sampling algorithm has actually been around for a while. The basics or conceptual basis of this algorithm was there in 1933 paper by Thompson, where the multi-armed bandit algorithm is one of the first paper which discusses it. And the reason it has been around almost as a folklore is that it's a very natural and simple heuristics. Okay? It basically says that since what you do for learning and decision making, what you can do is think about when you want to learn the parameters, let's say mu I of different arms. Don't try to get an estimate about the parameters like a frequentist, but think more like a Bayesian. Think about getting beliefs about those parameters and updating those beliefs. So what does that mean? So let's say you don't know anything about what the mean of this arm is. So then you could put a very high entropy belief on it. You could say that the mean could be anywhere between 0 and 1 with equal probability. Okay? Then when you see a reward, let's say I see a high reward for that arm, then I update my belief and say that now I actually believe that the mean is somewhere to the right. It has a higher mean than I previously think. It could still be on the left. I'm not completely sure because I just saw one sample, but I shift my belief distribution to the right. If I see a low reward or a 0 reward, then I say that my belief has changed now, and I shift my belief distribution to the left. Note that you're not shifting your estimate. You are shifting your belief distribution. You still have some probability of believing that the mean could still be high, but you are higher probability of believing that the mean is low now. Okay? So now if you do this, then how do you exactly do this shifting? Is simply using Bayesian rule. Okay? So you update your belief using Bayesian rule. And now when you want to play the arm, since you have now a distribution over what the mean is rather than one estimate of the mean, you use these posterior distributions to pick the arm. And how do you use them? You play an arm with its posterior probability of being the best. So according to your belief, every arm has some probability of being the best arm. You play that arm with that probability. It's very important to note that this is not same as choosing a maximum likelihood based arm, right? You're not choosing the arm that's most likely to be the best, right? So for example, if I think that with high probability first arm is going to have a better mean than the second arm, doesn't mean I'll choose first arm. It means that with high probability I'll choose the first arm, and with low probability I'll choose the second arm. Okay? So I always play all the arms, except that I change the probability with which I play the arms based on how much I believe they can be the best. Okay? So why does it handle exploration-exploitation? So now the way it handles exploration-exploitation is through what I say is like the mode and the spread of the distribution. right? The mode or the mean captures exploration because the mean of the distribution will actually converge to the actual mean of your posterior. And therefore, like if let's say some arm has high mean, then this posterior distribution mean will also become high over time. So if you were to use only the mean to choose your arms, you would be doing exploit only. But what saves you is the spread of the distribution, spread of the posterior, because the spread of the posterior reflects your uncertainty about your estimate, right? So if you haven't played blue arm a lot, its posterior is going to look very much like uniform because you started from something like uniform. If you saw only like 1 or 2 samples, it will shift a little, but it will still look very much like uniform. It will have very large spread or variance or standard deviation, okay? Which will mean that you would not be sure whether it can be best or not. You might think it has a 60% chance to be not best, but also 40% to be best. So you'll give it a more benefit of doubt. So with 40% probability, you'll still play it even though its mean is lower. Okay, so your spread will give you the exploration. So here is an instance of such a technique. So let's just concretize this kind of a algorithm. So let's say I was starting with, let's say my reward distributions are Bernoulli with unknown parameters, unknown means. Then a very convenient way to capture your beliefs or to model your beliefs is use beta distributions. Why is this convenient? Because it will be just easy to update the posteriors, that's all. You can use other distributions, but this is just more simple. So to reflect that you don't know anything about it, you may start with a uniform distribution over the means initially. The nice thing about beta distributions when you use them with Bernoulli rewards is that if your prior belief is alpha beta, beta distribution with parameters alpha beta. Beta distribution is a 2-parameter distribution with parameters alpha beta. When alpha is higher, it has higher mean. When beta is higher, it has lower mean. Okay? So by Bayes' rule, what happens is that it's a conjugate distribution to Bernoulli. So if you observe a 1 reward from a Bernoulli reward distribution, then the posterior is known to be simply beta distribution with parameter alpha increased by 1. So exactly saying that you're shifting your mean of the distribution to the right. Okay? If you observe a 0, it's simply a beta distribution with parameter beta increased by 1. So it's a very simple update rule for your beliefs. Then based on that, you get this simple algorithm that if you want to solve multi-armed bandit problem, you start with a beta 1-1 uniform distribution. Beta 1-1 is same as uniform distribution. It has the same expression. So you start with beta 1-1 belief for every arm, arms mean, and excuse me. And for every arm I, you sample independently from your posterior. So because of this update rule, your posterior will always look like this, where the alpha beta parameters is number of successes, number of ones, and number of failures, number of zeros, okay, because of this update rule. So you sample a parameter from this posterior and play the arm with highest sample. So by doing this sampling, you are implementing this rule that you play every arm with its probability of being the best. Okay? You don't have to actually compute the posterior probability of being the best. To implement it, you can just sample from the posterior and play the arm with the highest sample. Okay? Because computing those probabilities could be messy. So then you observe the reward and you update the beta posterior that you have for the arm that you played. Okay. So that's the whole algorithm. You can define other versions of this algorithm based on other belief distributions and other reward distributions. Like it's more convenient to use conjugate priors because they're easy to update. So one example of that is Gaussian. So you can use Gaussian to represent your initial belief, standard Gaussian to represent your initial belief because it has enough variance, enough entropy. And then every time you see a reward, again, it has a very simple rule. If you imagine that your reward distribution is Gaussian, then the posterior after n independent observations from an arm is simply a Gaussian with mean as the empirical mean and variance as 1 over the number of observations that you have made. Okay? So it's very simple to update. And then again, the algorithm is the same. Every time you want to play an arm, you simply sample independently from each arm's posterior, and you play the arm with the highest sample. So note that it's not same as playing the arm with the best posterior, because you're not playing based on mu I hat, you're playing based on the sample from the posterior. So there has been a lot of recent progress, including some of my work, on proving guarantees about this algorithm. So as I said, this algorithm has been around for a while, but it was mostly taken as a heuristic. But in recent years, many researchers, including myself, have shown that this algorithm actually has very rigorous, strong theoretical bounds on regret. In fact, it can achieve the optimal lower bound, which is this. So the optimal constant for in the Lie-Robbins lower bound that I mentioned in the beginning of the presentation is this, which is this is the KL divergence between the optimal distribution and the suboptimal distribution, and delta I is the separation that I mentioned. So this KL divergence is roughly delta I squared, so it's very close to the UCB bound, but slightly better. But overall, the behavior looks like logarithmic for problem-dependent bounds and square root NT for problem-independent bounds. Okay? So I want to mention that even though we are talking about priors and posteriors, we are not in Bayesian bandit setting. Okay? I still assume that the arms could have any mean, there is no prior on them. I'm just starting with a belief representation as some very high entropy initial prior, right? A uniform distribution over the mean or a standard Gaussian over the mean. I'm not assuming that is actually the true prior. The regret is defined in worst case, not as expectation over prior. Okay. So I want to give a little bit of idea of how someone would prove anything about such an algorithm. How much time is there? 45 minutes, okay. So how would someone prove something about this? And because we already saw UCB, so you already have some background, and those deviation inequalities kind of thing will come into picture. But you'll see that it's slightly more tricky to prove things about this algorithm because it doesn't have this monotonicity property like UCB. So to handle this complex analysis, let's just focus on two-arm case. So let's say you only have a problem with the results are available for the general case, but here I'll just talk about two arms. So in two arms case, let's assume there is arm 1 and arm 2, and let's assume 1 is better than 2. Of course, the algorithm doesn't know that. And delta is the difference between arm 1 and 2 means. So again, to get the regret bound, I want to bound the number of pulls, the number of mistakes, which is now the pulls of arm 2, by log t over delta square, so that I can get a log t over delta regret bound. Same thing as UCB. Okay? Now, so then I want to know how much pulls of arm 2 I will do, how much Thompson sampling will make. Okay? So what is the nice case? As we discussed in UCB, if arm 2 has been pulled enough, things should be good. It should have nice concentration. But in this case, there is slightly more tricky thing is that just arm 2 having enough pulls is not enough. Arm 1 also needs to have enough pulls. Why? Because we don't anymore have that property that the estimate we are using is above the mean always. What are we using? We are using our beliefs, which will look something like this, and we are sampling from the beliefs, and we are comparing the sample to make a decision. Now this sample can be above or below the empirical mean, and therefore you cannot really argue that it will always be above the true mean. Okay? It can be anywhere. So now that whole property that UCB seemed to rely on is gone. You don't really have the fact that the sample I'm using is above the true mean. Okay? So I cannot, so I would like to say that once arm 2 has been pulled enough, things should be good. So what happens is, again, let's look at this scenario where arm 2 has been pulled enough and arm 1 has been pulled enough. That case is still good. Okay? If both the arms have been pulled a lot meaning this much, then we are still good. Why? Because after both the arms have been pulled a lot, then their empirical means are close to the true means, close meaning compared to their separation, and their posteriors are also well concentrated. Right? They have low variance, because variance depends on how many samples you have seen from that arm. Okay? So now their empirical mean is close to their true means for both the arms, if both the arms have been pulled enough, and their posteriors are concentrated enough so that the overlap between them is very minimal. Why do I want low overlap? Because now it means that if I sample something from this blue distribution, and if I sample something from this red distribution, then the blue samples is highly likely to be above the red sample. There is very little area, very low probability area where they cross. Okay? So it means that once both the arms have been played enough, they are well concentrated posteriors, then I'm good, I'm gold. Then I can say that the blue arm will almost always be preferred to the red arm if I take 2 samples from these distributions. Okay? So this case is good. But this case is not, not enough because I'm requiring not just the bad arm's mistakes to be 16 log t over delta squared. I want to say that good arm has also been pulled enough. But the whole idea was to show that good arm should be pulled enough. So how do I break this cycle? So how long will it take for the good arm to be pulled enough? Okay? What will happen before good arm has been pulled enough, and how long will it take me to get out of that scenario and reach that good scenario? Okay? How many mistakes of arm 2 might happen before arm 1 has been pulled enough? That is what I want to bound. So what is that scenario? So suppose red arm has been pulled enough, which is the case that I could handle in UCB, right? But arm 1 has not been pulled enough. Okay? How long is that period? So what happens in that case is that the red arm, the bad arm, has been pulled enough. Okay? It has well concentrated posterior. But the good arm, the blue arm, has not been. So it has a large spread. Okay? So there are 2 things that can go wrong in this scenario, unlike UCB. Okay? One, your mean estimate could be, for the good arm, could be lower than the mean estimate for the bad arm. Okay? Second, even if the mean estimate is okay, that still doesn't mean that you will not make a mistake, because your sample could be coming from here for the bad arm and here for the good arm. Okay? Your sample could be lower because the good arm is not concentrated where it should have been. Its distribution is wrong. Okay? So because of these reasons, I could still be making a lot of mistakes. With constant probability, I could be making a mistake because I could be getting a sample here for good arm instead of here. Okay? So how do we bound the number, how long it takes for me to get out of this situation? We use exactly the challenge that we are facing. The same thing that is causing us a challenge actually will help us. This spread is actually our friend. Why? Because of this spread of blue arms distribution, yes, I'm making mistakes. But because of this spread, I'm also sometimes, with a good probability, constant probability, taking samples from here, from the right. Right? I'm making mistake with constant probability because of this high spread, but also I'm getting very good samples with constant probability. So every constant number of steps, I'll have a chance of getting a very good sample from the blue arm. So after this times a constant, I will have these many pulls of arm 1. Because I cannot be waiting too long before making a pull of arm 1 because of this spread. So this spread gives benefit of doubt to the blue arm and actually gets me out of this situation of not having enough pulls of blue arm. And that's basically the summary of the proof for Thompson sampling. Of course, when you extend it to multiple arms, there's some more complexities involved. Okay. So are there any pressing questions that I should take at this point? Before I move to the second part of my talk, where I'll use these techniques to solve more extensions of the problem. Okay? Feel free to interrupt me if something bothers you. Okay? So now I will move on to some very, very useful generalization of this problem. So you might have noticed the way we define the basic multi-arm bandits problem seems a little bit unsatisfactory. There seem to be too many assumptions, like you pull one arm at a time, you only see reward from that arm, that the reward is always from the same distribution. Whenever you pull that arm, it's independent of the previous pulls. So there's lots of assumptions, which seems like none of the applications I started with might ever satisfy, right? So it is definitely the case that if we were to be able to solve only that setting, then it would be only of theoretical interest. Luckily, there has been a lot of very interesting work on taking these basic techniques, the same basic techniques, the two techniques I talk about, and then apply them to this very enormous set of problems which get rid of almost every assumption that I just mentioned. Okay? So one of the, I'll talk about 2 or 3 of them depending on how much time I have, but let me give you like a brief overview so that even if we don't get to them, you have where to look. So one of the main things that has been tremendously useful, and I have personally never seen bandits being used without this extension, which is the context-dependent reward. So what that means is that when you pull an arm, then the reward of the arm, we assumed it's coming from a fixed distribution always. Now you think about a very simple extension that when you pull an arm, it's coming from, the reward depends on the context in which the arm was pulled. So for example, if you show an ad to a customer, whether they'll click or not depends not just on the ad, but also on their customer preferences. So that's the context. Or if you offer a price for a product, depends on not just the product, how good the product is and how good the price is, but also it depends on what is the paying ability of the customer, how much they like the product, and so on. So that's the context. So this has been a very, very remarkable extension, and the useful thing about it is that it has been extended not by saying that the distribution can be arbitrarily changed with context. It's saying that it thinks about a parametric form which remains fixed, but the context changes and how context interacts with that distribution changes. So this has been very exciting. The second part is like this kind of assumption that you only pull one arm at a time and you see its reward. For that, there has been extension to assortment problems, where instead of one arm, you present an assortment of products, an assortment of movies, assortment of retail products to the customer. And their response depends on how they feel about the whole assortment rather than just individual products on that assortment, right? So if there is a very expensive product placed with a very cheap product, then my response to the cheap product or the expensive product might significantly be different than if 2 expensive products were shown to me together. So this kind of externality has been handled in bandit extension. Then a very, very genuine complaint could be that we are just thinking about reward maximization. What about resource constraints? What about other kinds of restrictions to what arm you can play? Even if you know that this is the best arm, you cannot play it all the time. You cannot show one movie to all the customers all the time just because it has the best response, right? You need to do other things. You need to have diversity. You need to have some kind of a resource constraints on how much product you can sell, inventory constraints, and so on. So there has been also very useful extensions to such constraints in bandits. And finally, this is something that has been taking off very recently, is that you could say that when you pull an arm, the response depends on the state of the system, not just on the arm. And that state also evolves based on your decisions. So imagine you were using sequential decisions for personalized medical treatments, right? So what kind of response you get for a treatment doesn't depend just on how good that treatment is. It also depends on what treatments were used for that customer, for that patient in the past. And due to those treatments, what is their current state? And that will affect the response to the same treatment on that same customer. So your past decision changed the state of the target, and that will change the response to the same action. And that's what we call reinforcement learning, or MDPs, learning MDPs, where you want to model the process not as IID distributions, but as a Markov decision process. And remarkably, even though this looks like a so much harder problem, the techniques of posterior sampling and the UCB that I mentioned have actually been shown to produce near optimal regret bounds for this very much more general setting. Okay, so let's see how much we can cover in the remaining time. I'll go through. I'll give a very brief overview of these topics, and if you're interested, you can look through the tutorial or go to the references I'll mention. So first topic is handling context. So how do we handle the fact that when I show a product, then the response depends not just on the product, but also the customer preference. So one very, very important assumption or model choice made here, which I think is what made this so much more useful than if they would have modeled it as arbitrary distribution response. Very important model choice made here is that when you offer, let's say, same product or the same arm for a different customer, you first get to see something about that customer. So that's an information point that makes it less arbitrary as to what their response is going to be. So this is what we call context. So you might see their profile or their past purchases. So some context that you get about that customer before you pull the arm. So now the main assumption is that even though your response to the arm could be arbitrary depending on that customer, customers with similar context will have similar response. Okay? So that gives you, that makes the problem much more tractable than having arbitrary number of arms depending on how many number of customers you have and so on. Okay? So this is the whole idea, and this idea kind of comes from the supervised learning linear regression framework. You think about modeling the context as features of the customers or the environment or the market that you are pulling in the arm in context of. And then you think about, can I learn the model by which the customer responds depending on the context? And this model in the simplest case could be a linear model with a fixed parameter. So that's the main idea. Something needs to be fixed for the techniques to be applied. So you don't fix the response model, you make it dynamic, but the parameter is fixed. The dynamic part just depends on the context. Okay? So you want to learn now a linear parametric model, or extensions to nonlinear parametric models are also possible. And based on this model, depending on the context, the response is going to be different. Okay? So let's make it more concrete. So the contextual bandit formulation is that now for every arm I, before making the decision which arm to pull at time t, you see a context for every arm. Okay? And the reward when you will pull an arm I will depend on this unknown parameter theta. The expected reward will depend on the unknown parameter theta and the context. So in the linear case, it will be a dot product. The expected reward is a dot product between the context and the unknown parameter. Okay? So then the problem is still similar. You still require to pull one of the arms, so effectively pull one of the contexts that were presented to you. And depending on which context you pull, your reward, expected reward is going to be xt transpose theta plus some noise, right? And main difference between is the one main difference is in the regret definition. So now since the optimal choice of arm, the product you want to show depends on the context, you don't want to compare regret against one single product. That would be too crude. Then you will be saying, if I had shown one single product to all the customers, what would be my one best product? That seems too low a bar. What you want to compare is for every customer, if I had shown the best product for them, I want the optimal to be that. I want to compare to that in regret. And that's how the regret is now defined. You compare, so if you knew this unknown parameter theta, then every time you see the context, you would choose the arm with the best x transpose theta. Okay? And my regret is defined with this optimal choice versus the choice I made, okay, for every customer. What saves us is that even though the choice I make, the best choice is changing with the customer, this unknown parameter is not changing with the customer. So even if you are seeing the effectively samples from different models, all these models have the same underlying parameter. that I can learn from these different samples. And that's why we will be able to use these same techniques. And the techniques basically derive, again, UCB and Thompson sampling both have been used in this context. The way they are derived is the same basic principle, except that now to build this upper confidence bound, you need to use a little more complex estimation techniques, right? Earlier, the estimation was just empirical mean. Now the estimation is some kind of a linear regression. You're trying to estimate the parameter of a linear model. So you do linear regression, and you don't need to go into this. If you have seen this before, it's just like least square estimate. So I can do a least square estimate of my linear parameter of my linear model based on the past sample. That would be my exploitation only estimate. For exploration, UCB would want to put a upper confidence bound on this parameter. Now, upper confidence bound is misleading because this parameter is not reward, it's a parameter. So you don't, optimistic doesn't mean it should be, the parameter should be higher. What you really want to do is you want to build a confidence interval around this parameter, and you want to build an interval where you have high probability of the actual parameter lying in that interval. Okay? And this has been done using, using some linear parametrics and confidence bound estimates. Okay? So the way UCB then just is extended is that the algorithm goes like this. At every time t, observe the context for every arm. Then you find the optimistic parameter estimate for every arm, right? So I know that based on my deviation bounds and so on, that the actual parameter lies within this interval of my estimate. Okay. Then for arm I, my most optimistic best estimate is some parameter that maximizes theta transpose xt within this confidence interval. Okay. But this is going to be different for every, this optimistic estimate is going to be different for every arm depending on the context. Now, I pick simply same as UCB, the arm with the best optimistic estimate. Okay. So Thompson sampling again uses similar ideas, similar least square regression estimate. And the extension is also very simple. Now, instead of saying that the belief that I'm maintaining, so earlier, if you remember in the basic setting, we are maintaining belief of on the unknown means of, let's say, Bernoulli distribution. Now, you maintain belief on what you don't know, which is this parameter theta. And how do I update those beliefs? Again, whenever I see an observation, because I know the context, I see an observation from theta transpose x, I update the belief about theta. Okay? And very simple update rule is obtained if you use Gaussian, because Gaussian has a nice conjugate property, even for multi-dimensional case. So you start with some standard Gaussian over this multi-dimensional parameter with identity matrix as their covariance matrix. And every time you see a reward, if you update the beliefs according to the Bayesian rule, a remarkable observation, which actually started our paper on this, is that the posterior is nothing but related to this least square estimate. The posterior is the Gaussian with parameter exactly as this least square estimate as mean, and this covariance matrix from the least square estimate as covariance matrix. So based on that, every time you make an observation, you have simply the same least square estimate calculation to compute your posterior. And now, if you want to make a decision, simply sample from this posterior and use that theta to make a decision. So in fact, it's simpler than the UCB algorithm because you don't have to calculate a different optimistic estimate for every arm. You can simply sample one theta from the posterior and use it to make the decision. Right? In fact, in general, if the number of arms is large, which is where a lot of these problems are used, for example, if you have lots of products and you want to choose which product to play, then this, even though the regret bounds will not depend on number of arms, the computation problem is NP hard. Whereas in this case, since you have to sample only one parameter, this is much more efficient to implement. Okay, so the algorithm looks like this. Every time you want to make a decision, you sample from a Gaussian with mean as the least square estimate of your parameter, and variance as the covariance matrix that appears in the least square estimate. And once you have the sample parameter, you just pretend that's the real parameter and choose the arm that you would have chosen if you had known the real model. Okay? And that's all the algorithm. The sampling ensures that you are doing some exploration. It's as simple as that. Okay? Of course, since the Thompson sampling algorithm is slightly more efficient, you pay for it in the regret. The UCB version, which is also called lin UCB, gives you a d square root t regret, whereas the Thompson sampling algorithm gives you d raised to 3 by 2 square root t, where d is the dimension of this parameter theta. Okay? In fact, there is one interesting open question, which I don't know if anyone is working on or interested in working on, is that there is no, in my best of my knowledge, there is no efficient algorithm with d square root t regret in this case. So this is d square root t, but it doesn't get you, this is not an efficient algorithm, meaning polynomial time algorithm, but this is polynomial time, but the best regret bound is d raised to 3 by 2. Okay? Just a nuanced problem. Yeah. Okay? And this is matched by the lower bound of d square root t from in the literature. How much time do I have? 20 minutes? Okay. Yeah, so I can spend five minutes on 2 more extensions and then conclude the talk. So there have been a number of different formulations of contextual bandits, so beyond linear, much beyond linear. So you could have the response depend on this unknown parameter and the context, where the dependence on context could be convex. It could simply be some Lipschitz function by which the response is determined, and it could be generalized linear functions. So there has been tons of work. So if you have some kind of response that depends on a context and looks like a very complex function, look for it. It probably is handled by one of those extensions. Okay, okay, so the next little piece of work I want to talk about is assortment selection, right? So the retail application was star, and like there it's very common to offer more than one arms at a time, more than one product. And then the issue is that depending on what set you choose, the response of the customer for the same product could be different, right? So for example, if you were to show these 3 headphones, which are not that different in the cost, but then you add this 4th one, which is very much lower cost, then suddenly you're thinking, why am I paying this much for something which doesn't look that different, right? And even has worse reviews, actually, right? So suddenly your idea of how good they are changes because of this new thing, right? Same way, if you were to recommend shows, then depending on what show is popular, this response to other shows might change. I used to show this before the final season came in, but it's fine. And so how do we handle this issue that your response can be arbitrarily biased for the same product or the same arm, depending on what it was shown with? Now this can become a very intractable problem, because now to learn about a product, you might have to show with every other possibility to figure out what is the real response to it, right? Showing it alone may not be option in most of the cases. You cannot show just one product to figure out how customer responds to it. So what do we do? Like, do we show it with every other possibility? That seems intractable. So you need some structure on how the customer responds to this kind of a choice presented to them. And that structure will help you make the problem tractable. Obviously, none of these structures would be ever agreed upon. As someone said, all models are wrong, but some are useful. So this is a very, very useful model that has been very popular in operations research, which is called multinomial large choice model. Okay? And this is what has been used in Bandits. So the idea here is to restrict a little bit, provide a little bit more structure on how customer responds and processes these multiple different products presented to them. So we assume that when assortment is presented to them, they their proportional response to the product doesn't change, right? So if they were preferring product 1 to 2 before, they still prefer product 1 to 2 in the same way, okay? But maybe they prefer both the products a little less because of this third product, right? Or a little more. So the proportional response between the relative response doesn't change. So that is also called independence of irrelevant alternatives. And this is the precise mathematical formulation of the probability of choosing a product I by a customer when a set of assortment S is presented to them. Okay? So this expression basically models the fact that the relative probability Pi versus Pj remains the same, irrespective of what other products are present in the assortment. Okay? If you divide Pi versus Pj, it depends only on theta I and theta j, and not on the other products. So in this case, a useful thing is that if you think about the assortment problem, the problem itself could be intractable if the choice was arbitrary. If I didn't know how the customer would respond to a different set of assortment, I wouldn't even know how to pick a good assortment, even if I knew all these probabilities, right? In this case, when you have restrict the probabilities like this, then you are able to at least choose the offline problem. I mean, when you know the model, at least you know how to select a good assortment of size k from it. Okay? So that should be like the first check. If you can't even solve the offline problem, when you know everything about the model, then there's little hope of solving the learning and the online problem, right? Now, how do we solve the problem if you don't know these parameters underlying the choice model? So then the bandit problem, which we introduced in a few years back, was that now the problem is that in every time t, instead of pulling an arm, you pull an assortment. You observe, in addition to the revenue, you observe what the customer chose. So you get a feedback on the choice model. And using that, you can update the estimates of your parameters of your choice model. The goal, as before, is to minimize regret. But now the regret is compared to the optimal assortment you should have ordered if you knew the choice parameters underlying the model. Okay? So again, you will see a common theme that the way the problem has become intractable and we are able to use bandit techniques is because we have taken this thing which seems much more complex and reduced it to learning these parameters, these fixed parameters for which our samples will give us some information. And we will update the estimates of these parameters using UCB or Thompson sampling, and then use those estimates to make decisions as before. So the main techniques here, the main challenge that this faces is that like the hurdle that you have to go over before you can apply UCB and Thompson sampling is this issue of the bias in the sample, right? So if I presented a product with a lot of different products which are also attractive versus unattractive products, then I'm seeing a different response. So how do I glean out the product's own merit from these two different kind of scenarios? And one of the main techniques we introduced was this overall overarching technique that at least works in the MNL model, is that what you can do is you can do this offer an assortment until no purchase, and then the number of times it takes until I is purchased will give you an unbiased estimate of the parameter for product I. I won't go into details of that, but you have to cross this one hurdle to get an unbiased estimate for individual parameters, and then you can use the same techniques as we had for regular bandits. Okay? And let's skip the regret bounds. I want to briefly mention this very, very useful extension, which has very far-ranging applications. So here, we come back to like the basic question in OR, like there is not just reward. There are constraints, there are resource constraints, there are constraints on time, there is constraint on inventory. So how do we incorporate that? Even if you think one product is really good product, you cannot sell it to everybody, right? Or you cannot recommend the same movie to everybody. So how do we incorporate these additional considerations into bandits, right? How do we get over the fact that you're just finding one optimal arm? Okay. So this extension talks about how do we put additional constraints on the on the rewards and the cost that you see when you pull an arm. So these kind of things appear in a lot of places, like every possible application that I talked in the beginning, you can think of such constraints. Like in advertising, there might be budgets associated with advertising. Even if an ad is really good and everyone wants to click on it, the advertiser is just willing to pay for 100 displays. So even if you figured out it's the best one, you cannot show it forever, right? So same way, every network revenue management, even if the product is really good and you can price it really high, there's only so much inventory available for it. Okay. And same way, you could have beyond sum of rewards. You could be saying that I don't want to optimize just the reward. I don't want to maximize the clicks on my movies. I also want to give some diversity of the movie so that the customer will come back and find this place interesting, right? So you want to change the objectives also in this way. So number of useful extensions. So one of the initial extensions was on thinking about simply constraints in terms of cost. So what if whenever we pulled an arm, we observed a reward, and for every resource J, we also observed a cost, okay? And that cost depends on the arm pulled and the resource, okay? So in addition to doing this, which we do always in the bandits, you're also trying to make sure this, which is the universal global constraint on the total cost that you get by pulling these arms, okay? A more general extensions was given in our 2014 work, where we say that you could just be observing some arbitrary vector instead of one number when you pull an arm, and you could have some arbitrary function of this vector that you want to maximize of the aggregate vector, and some arbitrary constraint set where you want the aggregate vector to lie. So a lot of nonlinear rewards and constraints can be modeled this way. I'll skip over the techniques, but again, the idea now is to construct confidence intervals over these vectors instead of individual rewards. Okay. So I want to mention a little bit about where these techniques, the exciting directions in which these techniques have been going recently, and where there's a lot of scope to do a lot of interesting work. So one of the exciting directions, in my opinion, is this something we call reinforcement learning, but I think reinforcement learning is somehow has become a very daunting term for something very large scale and flashy. But I think we have lots of problems, what we call MDPs, where there is some kind of states associated with maybe due to inventory state or customer satisfaction state. So some states that change with taking the decisions. And now the bandit problem, if you still want to formulate it as bandit, it's simply saying that, well, I don't want to learn just the reward model. I also want to learn how the state changes with my arm, right? So again, if you think about the more general view, as we talked about in contextual bandits and so on, if I could have like a parametric model for how the state changes as well as how the reward change, then I'm still learning some parameters. So I could still use Thompson sampling to put a belief on those parameters and update those beliefs based on how I see the reward sample as well as how I see the state change. So I'll do one more update. I will update both my reward parameters as well as my state transition parameters based on the state transition that I saw. So the basic concept still remains the same. And then if you make your decision taking by sampling these parameters from the posterior, a posterior belief instead of just the estimate of these parameters, then you will ensure that you explore the space of the parameters enough. And in fact, this concept we use to show that you can get for arbitrary finite state action MDPs, you can get near optimal, very rigorous regret bounds using the same bandit techniques. And other people have also showed that UCB-like techniques can also be used by viewing the state transition model as another set of parameters that you want to learn from your observation in addition to taking decisions. Okay. What I think is even more exciting is thinking about not finite state action MDPs. So finite state action MDP is not just about finite. The regret bounds actually depend on number of states, which is obviously not going to be very useful if you're thinking about continuous state, like even inventory states, which could be high dimensional and continuous, so number of states could be very large, but which have a lot of structure in them. So one of the recent works by us and other researchers, we show that this structure can be actually used to reduce the problems to some known bandit versions. So for example, in one of the inventory control problems, a lot of inventory literature has shown that the long-term average reward is convex in the decision policy. Now we show that if you do discretization like here, you lose all that convexity. So don't do discretization. Instead, think of it as a convex bandit problem. And then we show you can use convex bandit algorithms to solve that problem instead of going to reinforcement learning. So this is another line of interesting work, which I think has a lot of scope because there are a lot of structural results on MDP for many operations management problems. Okay, so to leave some time for questions, I will just summarize the presentations. So the summary of the presentation is that so the multi-armed bandit problem, which starts with a very cute, simple mathematical formulation, has been extended to handle lots of useful and general models for sequential decision making. And the main thing that makes them tick is that the algorithmic techniques have been really simple and elegant. They can be used with very little, and they have been used, according to my personal experience, with very little tinkering with the way they look, because they are very simple. And they also work remarkably well in practice, actually. In addition, it's very rare to have very good theoretical guarantees for such techniques. So if you want to take away one thing from it, next time you have a decision-making problem which involves some learning component, and you're wondering, will I be able to learn while making decisions? Think about bandits. I'm sure you'll find some formulation that fits your problem. Right. Thank you. Yeah.
So are there any advantages in using techniques in adversarial multi-armed?
Yeah, so I was hoping I'll get that question because I didn't have time to discuss that. So there's another set of bandits which I didn't discuss at all, is adversarial bandits, where you don't assume there is any stochastic process by which rewards are generated, but the rewards could be an arbitrary sequence. And the way it is handled is that you relax your regret a little bit and you say that I will compare to the best single arm. Even though it's not optimal, I'll compare it to the best single arm. Now there is a very interesting technique which applies both to stochastic and adversarial bandit, is the multiplicative weight algorithm or EXP3 algorithm, and it has very good it has a very good instance independent bound, the sublinear bounds. Barring some very recent developments, it didn't have the logarithmic bounds that Thompson sampling and UCB provides. But yes, recently there have been progress in using regularizers that give you logarithmic bounds. So they are kind of converging. So I don't have the answer yet. Before there were no logarithmic bounds, the answer was, in practice, the behavior you see for regret matches the logarithmic more. So the sublinear bound seems like a very crude bound to understand the performance of the algorithm. So therefore, I would prefer something like Thompson sampling and UCB. But if you use a technique which can give logarithmic bound for adversarial, then it's great, yeah. I think the question is like, what technique gives you regret growth that matches what you see in practice? And I feel like that closest is Thompson sampling. It comes closest to seeing the kind of the performance you see in practice, but UCB is also pretty close with careful tuning. Yeah. Mm-hmm. Yeah. So good question. So the question is like, what happens if the reward distribution is changing over time, or the rewards are not IID? So first of all, like contextual bandit is like handles one case where it's not IID, because now the same arm could be producing a different reward distribution depending on the context. So I find that even though it seems cheating to some people, but I feel like in terms of practice, it's actually a very, very useful extension, because you still feel there is a pattern, right? It's not arbitrarily changing. The pattern is how the customer preference changed from one customer to another, and it captures that change into how the reward distribution changed. So I think contextual is one example of the fact that the same arm has a different distribution depending on the context. But there's also more general works where you limit, which I didn't cite here, but there is general work where you limit the budget of change in the distribution, and then depending on that budget, you can bound regret. So you say that the distribution can change arbitrarily, but within some limit, and depending on how big that limit is, you'll get better or worse regret.
One last question.
Yeah, sorry. We can take it offline. Yeah. Oh, yeah. So I didn't discuss that extension. There's so many different. So instead of measuring regret, you could be measuring something else. So regret says that I care about the reward you get while making these decisions, not just what you learned in the end. You could also care about just what you learned in the end instead of caring about everything you did to learn that. So that's slightly different setting. It's more about the learning and the exploration, efficient exploration. So it's more of the what we call active learning or simple regret. Some techniques, similar techniques work, but there is subtle differences, because you're more worried about when to stop, and rather than how to make sure that you are not pulling arms which are too bad. Right? The trade-off is not exactly present there. Yeah. Okay. You want to take it offline, or yeah? Okay. Yeah, I'll be here for a few minutes, yeah. Thank you. Thank you, it's been a pleasure.